Ja, das habt ihr sehr schön hinbekommen, gefällt mir sehr gut. Das Engineering schaut sauber aus. Freut mich. Dankeschön, Herr Stocker. Meine sehr verehrten Damen und Herren,
Hello, today I would like to talk to you about the core component of our Power Exchange technology platform. This is the lithium-ion battery cell that is installed in our power packs. This episode will look in detail at battery chemistry, for example the electrochemical processes that take place in battery technology.
etwas länger.
As a result, it will be slightly longer than the other episodes.
Ein Kurzüberblick.
If you would prefer a shorter overview of the battery platform, you can see a concise summary in episode 1. In episode 3, we will introduce the battery packs, again in the form of a concise summary, and episode 4 will provide a short overview of the charging technology.
Mein Name ist Dr. Markus.
My name is Dr. Markus Thannhuber, and I'm responsible at board level for the areas of quality assurance, technology and production at Einhell. Today I would like to take you on a journey into the world of the battery technology used in Power Exchange battery packs.
Battery Packs.
Power Exchange receives its power from lithium-ion cells, the most modern and stable cell technology that can be manufactured today on a large scale.
Ionenzelle. Lithium.
Here, lithium is a very special element.
Das ist ein Alkalimetall.
It's an alkali metal in the second period of the periodic table of elements and has the atomic number 3.
Protonen. In den meisten
This means that it has 3 protons and in most cases 4 neutrons, or 3 neutrons in rare cases and 3 electrons. The innermost shell 1s is therefore full with 2 electrons. However, there is an additional sole electron in the 2s shell.
Orbital alleine. Das ist energetisch.
This situation is unfavorable in terms of energy, and this is the reason why lithium is highly reactive. It attempts to combine with reaction partners in molecular compounds to achieve a more favorable energetic configuration.
Zielen in Lösungen.
In solutions, the 2s electron is very quickly stripped away. As a result, lithium is always present as a positive lithium ion, and it is reduced very significantly in size in the process.
Größe. In der Konsequenz.
This means that lithium has a very low electronegativity, so it is strongly electropositive.
Gleichzeitig und
At the same time, particularly because of its small size, the lithium ion has an extremely low redox potential. In fact, it has the lowest of all chemical elements at minus 3.04 volt.
4 Volt. Das macht Lithium 1.
This makes lithium unique for the production of rechargeable batteries because it allows high cell voltages up to 3.6 volt in today's configurations. By contrast, lead-based cells only permit a cell voltage of 1.75 volt and nickel-based cells like nickel-cadmium just 1.2 volts.
Nachdem der gespeicherte Energieinhalt
Since the stored energy content E of a cell is equal to its capacitance C multiplied by the cell voltage U, the energy that can be stored in rechargeable batteries with the same capacity increases linearly with the cell voltage. And this means that, like for like in terms of capacity, lithium cells offer the highest energy content in comparison to all other cell systems, namely up to 300% more than the energy content of nickel-based cells, and therefore plenty of power for any sort of tools. All this means that lithium packs a real punch for battery cells. Although this power needs to be controlled, at the same time it offers unique opportunities.
Das Grundprinzip elektrochemischer Zellen wie der
In essence, the fundamental principle of electrochemical cells like lithium-ion secondary cells, which is the full name of a rechargeable lithium-ion battery, is to physically separate a reversible chemical redox reaction, capture the charge exchange that takes place in the process and carry it to the outside.
zu fassen und extern zu führen. So reagiert beispielsweise bei vorliegenden Reaktanten
For example, lithium intercalated in carbon as the first reagent and a metal oxide as the second reagent react under the presence of reagents to form the products lithium metal oxide and carbon.
und Kohlenstoff als den Produkten. Diese Reaktion ist
This reaction is driven solely by chemical potentials, and without the physical separation it would take place under release of large amounts of heat, but without delivering any electrical energy.
elektrischer Energie erfolgen.
If the reagents are physically separated by means of an electrically non-conductive membrane, the so-called separator, which permits no flow of electricity but allows lithium ions to pass, the reaction space is filled with an electrolyte in which lithium can dissolve and move freely, and the reagents are delivered to 2 electrically conductive foils on which electrical charges can accumulate, and be fed in or be conducted away. This will result in a chemical reaction that no longer takes place in a direct and uncontrolled manner.
Vielmehr findet die Reaktion
Instead, the reaction takes place as follows. Positive lithium ions are dissolved and migrate through the membrane to the metal oxide to the same extent and in the same quantity as electrical charges and electrons migrate via the electrical conductor and any connected consumers from the carbon side to the metal oxide side.
zur Metalloxidseite wandern. Und schon haben Sie
This is a battery, a so-called electrochemical cell.
elektrochemische Zelle. Die beiden
The two conductors immersed in electrolyte and coated with the active material are referred to as the electrodes. The carbon side that delivers electrons during discharging is called the anode, or specifically in this case the carbon or graphite anode. The metal oxide side is called the cathode, or in this case the metal oxide cathode. The processes taking place happen almost in isolation on each side and discharge the cell, thereby depleting the reagents that provide the chemical drive for the reaction. At the anode, lithium is present that is intercalated in carbon. Here, the lithium goes into solution as positive lithium ions. One electron flows through the electrical conductor and carbon is left over.
Es verbleibt Kohlenstoff übrig. Auf der Kathodenseite
On the cathode side, the cathode captures both the electron and the arriving lithium ion, resulting in a lithium metal oxide.
und es entsteht ein Lithium-Metalloxid. Dies läuft so lange, bis das in
This process continues until the lithium present in the anode has left the anode and the cell is discharged as a result, or until the electrical conductor is interrupted,
Leiter unterbrochen wurde,
causing the positive lithium ions that are arriving at the cathode to force a growing separation of charge and therefore an increasing electrical potential,
mit einem anwachsenden Potenzial
which
führen
ultimately stops the migration of positive lithium ions.
unterbindet. Umgekehrt wird eine elektrische Spannung
In the reverse case, if an electric voltage is applied that strips electrons from the cathode, then these electrons are missing for chemical bonding of the lithium, which causes the lithium to go into solution in the form of positive lithium ions and migrate to the anode due to the difference in potential. Here, the intercalated lithium migrates into the cells framed by the graphite, and the two reagents are available again in their original state.
wieder wie ursprünglich verfügbar. Die so geladene Zelle
Once it has been charged again in this way, the cell is available for many further discharging and charging cycles. This is how simple the theory is that explains how the extreme chemical properties of the lithium cell, the small size of the positive lithium ion and its resulting mobility, as well as the associated extremely high redox potential, provided with its internal mechanism that drives the reactions. However, in practice, these extremes present us with a number of technical challenges that need to be overcome.
gilt. Zum einen
On the one hand, it is absolutely essential that we avoid metallic lithium in commercial secondary cells under all circumstances, simply because of its aggressive reactivity and the manner in which it forms, namely in pointed, needle-shaped structures, and the associated potential hazards. The entire discharging and charging process is technically designed as already explained, so that lithium is only present in compounds, intercalated or in ionic form, but never in metallic form.
vorliegt, nicht aber in metallischer Form. Eine weitere
Another challenge is the issue of the correct choice of electrolyte. Normally, for example, in lead or nickel cell systems, electrolytes based on aqueous solutions are used. That is not the case here. The nominal voltage of 3.6 volt and charging end voltage of up to 4.25 volt would cause electrolytic destruction of water and, in some cases, result in the production of dangerous gas mixtures. Hence, water is replaced in lithium-ion cells with voltage-stable organic solvents.
Leider sind
Unfortunately, these are highly reactive themselves and threaten to disintegrate the active materials, in particular the carbon graphite coating of the anode.
der Anode. Aus diesem
For this reason, we resort to a technical trick, surface passivation, which takes us straight to SEI, solid electrolyte interface,
sind, welches im Besonderen
which is one of the critical elements of lithium-ion technology and plays a very important role, particularly for high-power batteries. Through the use of suitable, specially selected organic solvents and the use of matching additives, after filling and the so-called cell formation, a passivating surface film forms on the anode. This protects the electrolytes against reduction at the anode surface and the anode against co-intercalation by the electrolytes. Nonetheless, the ionic transfer through the surface still needs to take place quickly and effectively in order to avoid an increase in internal resistance, and so that power can be delivered quickly and fast, charging and discharging processes are enabled. Many of the processes in the cell depend on motion at molecular and atomic level, on diffusion processes, acceleration due to repulsive or attractive forces in the electric fields of electric charges, and last but not least on the kinetics, for example the reaction speed of the chemical reactions taking place. The technical layout, state of charge, existing potentials at the electrodes and ambient conditions such as the temperature all play a part in defining these speeds and therefore the maximum energy that can be released or the ability to absorb electrical energy during charging. This is referred to as the so-called electrochemical metabolism of the cell. It is important that lithium-ion cells are used in such a way that the dissipated currents, temperatures, voltages, etc. do not overstrain the metabolism. If this were to happen, it would invariably result in destruction of the cell chemistry, potentially with fatal safety-related consequences. If, for example, the cell metabolism is overstrained during charging and too much current is delivered to the electrodes, then, figuratively speaking, we will get a traffic jam of positive lithium ions at the SEI. The SEI is then no longer capable of transferring the positive lithium ions quickly enough to the active material of the anode. On a smaller scale, this is certainly not a problem, but on a larger scale and over larger surface areas, this will invariably cause the pent-up positive lithium ions to be supplied with electrons. The result of this is that the accumulated positive lithium ions are suddenly precipitated as metallic lithium at the surface of the anode. For example, the notorious process of lithium plating occurs. Highly reactive, the metallic lithium itself reacts with the electrolyte. A passivating surface layer between the lithium and the electrolyte is produced. In this process, electrolyte is lost. The reaction products, including explosive gases, contaminate the cell chemistry. In addition, under certain conditions, the separated lithium forms a film that is not flat but instead grows in microscopically sharp needles, so-called dendrites. These can penetrate through the separator and, if they come into contact with the cathode, cause internal short circuits and the cell known as soft shorts. If the voltages between the electrodes are too high, the cathode material breaks up under release of oxygen. In addition, the organic solvent disintegrates electrolytically under release of gases, some of which are highly explosive. Likewise, if the voltage differences between the electrodes are too low, a situation known as deep discharging, degenerative chemical reactions take place in which explosive gases can be released. In addition, metals from the anode base, usually copper, can dissolve in the electrolyte. During the next charging process, these grow into needle-shaped structures on the surfaces in a similar mechanism described for lithium. If these needles penetrate through the separator, this results in severe internal short circuits in the cell, so-called hard shorts. If temperatures are too high or too low, this can also destroy the cell. For example, under excessively high temperatures, the SEI will be destroyed. It is immediately recreated in a reaction between carbon and the electrolyte. Unfortunately, this is an exothermic reaction, which means that heat is released in the process, thereby raising the temperature even further. At higher temperatures, still the cathode, which is highly sensitive to high temperatures, decomposes under formation of oxygen. In addition, the separator can also be damaged in the process. Low temperatures slow down the speed of diffusion and the metabolic rate in the cell.
Und den Metabolismus in der Zelle. Dies führt zu Folgen.
This leads to the consequences we have already discussed.
Es wäre hier
I could talk even more about here, but at this point it is enough to mention some of the key facts as examples of the problems that need to be neutralized and adequately taken into account via the technical solutions that are implemented.
der technische
The technical layout, cell chemistry used, enhancement with additives, physical parameters, heat management, etc. all have an impact on the metabolism and underline the sensitivity with which a cell responds to individual stresses and pressures. So what exactly does this technical layout look like?
Die Anode wird
As a technical solution for the anode, graphite is applied to both sides of a copper foil.
aufgetragen wird. Die Kathode dadurch, dass ein Metall.
Metal current collectors, the so-called tabs, are formed on both metal foils.
Beide Metallfolien werden Metallstrom ableiten
These collect the charge and transport it to the poles of the battery.
an die Pole der Batterie weiterleiten. Diese
They also help to dissipate the heat that builds up.
zu unterstützen. Zwischen die beiden Elektroden
A plastic polymer film is used between the two electrodes. This electrically isolates the two electrodes from each other, but also has tiniest pores to enable the flow of ions.
zu realisieren. Die Stripes werden so
The strips are then rolled up in a defined manner and inserted in a can. The anode tabs are soldered to the can base to form the subsequent minus pole of the cell.
Pol der Zelle. Die Kathoden-Tabs werden
The cathode tabs are soldered to the cap of the battery and form the subsequent positive pole of the cell.
den Pluspol der Zelle. Die Dose wird
The
sodann
can is then filled with electrolyte. Care is taken to ensure that no air bubbles remain in the can and that the electrode roll is fully soaked with electrolyte.
vollsaugt. Die
Here, the active materials assume a gel-like consistency, which is why the roll in the can is referred to as a jelly roll.
Jelly Roll bezeichnet. Anschließend
Afterwards, the cap is set on the can and sealed with a crimped flange.
verschlossen.
This is followed by the formation of the cell via special current profiles, through which the SEI is formed in a defined manner.
Nun wird die Zelle mit
The cell is then covered with an electrically insulting protective sleeve, which is followed by the so-called capacity breeding stage and a safety check over several days before the battery cell is ultimately finished.
vorliegt. Diese ist dann
This is then ready for installation in a Power Exchange battery pack.
Pack. Grundsätzlich
A wide range of different lithium-ion cells is available. Small, large, long, short, fat, thin, cheap and those that cost a fortune. However, only very few of them are actually genuinely suited to power tools.
aufgrund des
Due to the slowness of the metabolism described above, lithium-ion cells were predominantly used for applications in which long or even an extremely long service life was vital. Notebooks, camcorders, cell phones. All of these applications share the requirement that they are designed to run for a very long time and that their current draw is very uniform and very low in comparison to power tools. These cells are tailored for high capacities, low rates of self-discharge and inexpensive prices. They have been and still are manufactured in huge numbers and are available at very low cost.
Power Tools sind
By contrast, power tools need to offer extremely high performance, which demands a power supply in the form of a current with a more or less constant voltage.
die Profile der
The
Strom
current draw profiles for power tools typically tend to follow this type of curve here. What is particularly noticeable here is the high mean current draw along with the extreme current spikes, which are up to 100 times higher than those associated with electronic applications such as cell phones.
beispielsweise Telefonen. Für
For power tools and power garden applications, the high capacity of lithium technology is initially great, but the capacity of the batteries is not the actual limiting factor. Instead, this is the performance capacity, the power output in watt. When working with a handheld circular saw, for example, or an angle grinder, you will require huge amounts of power in the moment of cutting. In these applications, the batteries need to be able to discharge in a matter of a few minutes. However, since each process only ever lasts a few seconds, you can keep working for long enough with a tool. It's also important that the battery can be recharged quickly enough to enable continuous working with two sets of rechargeable batteries. This in turn requires a completely new approach to battery cell technology. For power tools and therefore for the power exchange battery system, Einhell's primary concerns are accelerating the cell metabolism, reducing internal resistance and optimizing internal heat management in the cell. This enables us to deliver battery cells that handle medium currents well and, in particular, safely. But what does this mean? In order to develop really good batteries for power tools and power garden tools, it is not enough to simply incorporate more active material in the cell, as has been done in the past, and to minimize everything else that represents the structure of the cell, shorten the strips and make them thicker, etc. No, instead it is necessary to significantly improve the distribution of the active materials, shorten electrolytic distances, increase surface areas, optimize the number and location of the tabs, and improve their heat dissipating capacity. The form factors also need to be optimized. This invariably leads to more delicate structures and thinner coatings that need to be applied homogeneously. The bonding of these with the electrodes base plays an ever increasingly important role. This requires better systems for coating and processing, for coiling, the technical process of coiling up the electrodes, as well as for electrolyte filling. In some cases, this means that new materials are required, but it also means that new process control approaches are required. For example, in the performance of the formation process for optimized formation of the SCI. We have discussed the things we do to make sure that we have good and safe control over the medium currents of power tool profiles. However, this alone is not enough to make a power tool run with a superior, satisfying performance. As has already been clearly shown, there are numerous peaks in the current profile of a power tool that are significantly higher than the mean current draw, so-called surge, spike, and peak currents. These are due to the fact that power tools are electromotive applications involving the acceleration and braking of masses to and from high rotational speeds and linear speeds. The huge forces and torques occurring in the process act largely in an undefined, unpredictable and sudden manner. Whether a nail in a board, a stone in the grass, a chip that becomes wedged between workpiece and tool or similar. Even startup acceleration and braking lead to huge spontaneous power demands or even backflow. All of these situations can be described as brief but intense. To get straight to the point, however hard we may try, no efforts to accelerate the cell metabolism will enable a lithium-ion cell of suitable size to cover these extreme spikes. The diffusion and reaction speeds are simply not sufficient for this. However, at this point, a very important electrophysical property of the cells comes into play. Basically, the technical layout of a lithium-ion cell is very similar to that of a capacitor. An electric capacitor consists of two plates that are parallel to each other. When it is charged, charged particles migrate to the two plates. Due to the potential effects of the charges that face each other on the plates, but which, due to the presence of a non-conductor, which is the dielectric in the capacitor, have no outlet for a direct charge exchange, there is, figuratively speaking, an urge for as many charges as possible to be facing each other when an applied voltage is present. The capacitor stores energy in the form of electrical energy on the plates that face each other. The larger the surface area of the plate, the shorter the distance. The more effective the dielectric, the greater the amount of stored energy. Unlike in a chemical cell, there are no secondary processes at all here, such as the diffusion of chemical reactions for the absorption or discharge of the electrical charges. The system responds immediately to voltage changes with currents that are only limited by the ohmic resistances or by inductive effects. In fact, the lithium-ion cell is a small capacitor. Here, the cells benefit from one special effect in particular. Charge separation occurs at the boundary surfaces between the electrolyte and the electrodes, resulting in a buildup of ions. Here, the charges with opposite polarities are opposite each other, separated by a tiny distance. This corresponds to the technical layout of a dual-layer capacitor EDLC, a form of capacitor that offers a particularly high capacity. Consequently, the electrochemistry of the lithium-ion cell unfolds a potent dielectric effect if the cell is designed accordingly. This is exactly the effect that is required for high-quality operation of modern power tool applications and for demand-driven coverage of the current peaks. The cells chosen for the Power Exchange battery packs have been developed to take advantage of this effect effectively and safely. The requirements of the dielectric mechanism are similar to those of the electrochemical processes. The actual application in the battery pack needs to employ a battery management system known as the BMS to ensure that the full potential of the cells can be safely taken advantage of. Overstraining due to overloading of dielectric capacities results in non-homogeneous current paths in the electrodes, with localized thermal overloads and overstimulation of the electrochemical metabolism as it is forced to follow the demands. Einhell takes this into account with fast current profiling for surge, spike and peak currents, our so-called SSP profiling. As the current profiles of power tools and garden products place significant demands on the cells, numerous technical safety features are integrated in all Power Exchange cells. For example, every cell has a so-called circuit interrupter device, CID, which monitors the internal cell pressure. Above a defined internal cell pressure, a so-called pressure disc deforms and disconnects the cathode connection to the positive pole. This interrupts all flow of current into and out of the cell. In addition, every cell also has two independent systems for controlled and part-controlled pressure reduction. These are the gas valves and the crimped closure, which acts as a predetermined breaking point. If the gas valves are unable to allow the gases to escape quickly enough, then the crimped closure opens. The separator is one of the most critical elements in the cell. It must avoid internal short circuits in the cell. In the process, it has a thickness of just a few micrometers. Triple-layer polyolefin separators are used in the Power Exchange cells, which ensure ion conductivity with their microscopic pores. These pores play an active role in order to protect the separator and therefore the entire cell against thermal overloading, for example, excessively high temperatures. They melt and close the separator, as a result of which the flow of ions through the separator is interrupted. In addition to this, a number of additional cell stabilizing additives are used, for example, proton inhibitors and polymerization additives. As part of cell qualification and ongoing quality assurance, we test the effectiveness of our safety concept and of the safety systems in comprehensive laboratory tests that are conducted both in-house and at the labs of renowned European university institutes. Unfortunately, to date, the requirements defined in the applicable standards in relation to cells and their safety have fallen significantly behind the rapid advancements of the technology. This will continue into the future. The usual qualifications obtained by testing the cells against EN or UL standards and via their certification are, of course, a basic requirement for responsible product developers, but, as explained, unfortunately, this is nowhere near enough. Today, the suitability of a battery cell for its intended purpose is not taken into account, whether or not the tool will overload the metabolism or dielectric mechanisms. In the past, this has led to the development of many power tools that are equipped with inexpensive but completely unsuitable batteries. Particular caution needs to be taken here. Latent risks can come to the fore after years of operation once degeneration of the cell electrochemistry becomes advanced and safety-critical reagents are present in the cell. Unfortunately, customers cannot identify unsuitable battery cells from perceived quality defects or poor performance. Last but not least, I would finally like to address the subjects of physical stability, cycle stability and cell aging. Here again, this is a topic that we devote considerable attention to at Einhell for our Power Exchange battery system. Cell aging is a specific phenomenon of lithium-ion cells. The inner clock of the cell starts to tick the moment the cell is filled with electrolyte. After a finite period of time, this aging process invariably leads to the death of the cell. We suspect that the main reason for this intrinsic cell aging is linked to the high reactivity of the organic solvents in the electrolyte, which can only be held in check through the technical formation of passivating surface films on the active material. Over time, microscopic defects will always occur in the passivation, which are then recreated. In the process, electrolyte, active material and lithium are lost. The thickened passivation films gradually become impermeable to the positive lithium ions, and the resulting reaction products interfere with the regular function of the cell chemistry. This aging is accelerated under high temperatures and under higher states of charge. The more effectively a cell has been technically developed, the larger are the active surfaces, and therefore the faster this aging process takes place. The chemical stability and, in particular, the thermal stability of the SCI are strengthened through the use of suitable electrolytes and additives. In addition, at Einhell we are very careful to ensure correct handling of the battery cells after production and during storage or shipment, which always takes place under suitable loading conditions. Cycle stability, for example, the number of charging and discharging cycles that can be performed, is also a significant factor in terms of the stability of the SCI. However, here we can have a positive impact on the effects of thermal damage with the aid of improved internal resistance and better heat management in the cell. In addition, with our Power X-Change battery cells, we always make sure that the physical processing of the cell is perfect and that the coiling process is optimized. In this way, we can ensure good cell stability even under high load requirements. Something that must be remembered with rechargeable batteries for power tools is the need to use physically robust battery cells. The packs will often encounter rough handling, bumps, knocks and vibrations. This alone has ruled out the use of lithium polymer pouch cells to date. The cylindrical windings and installation of the cell in round metal containers ensure that there is at least sufficient protection against direct external influences. The rest can only be ensured with very clean physical processing, which is something we place great importance on with our Power X-Change technology. I hope this has explained at least the main aspects of the cell technology behind our Power X-Change system. A good proportion of the secret of the high performance capacity and efficiency of Power X-Change thus lies in the lithium-ion power cells, which not only offer huge capacity but also extremely high power output capacity. We don't simply install off-the-shelf batteries of the type you would find in a notebook or camcorder. Power X-Change batteries are especially designed for use with and in power tools and electrical garden tools. They offer a very fast electrochemical metabolism, excellent dielectric properties and superior thermal management, which together enable high-performance working with the tools in the Power X-Change platform whilst ensuring maximum operating safety. This was episode 2. In episode 3, we will present the Power X-Change battery packs. Thank you for taking the time to watch this episode.
Dank für Ihre Aufmerksamkeit.